to have today Stefania to deliver the third lecture on the standard model. Please.
Okay, very good. Thanks for the introduction, and yeah, welcome back, everybody. So today, as I was mentioning yesterday, we talk about electroweak symmetry breaking, and then we'll discuss quite a bit, a little bit about the Higgs phenomenology. Okay, so that's the plan of today. So let's write it down. Plan, discuss. Let me abbreviate with electroweak symmetry breaking and Higgs phenomenology. Okay, that's the plan for today. So let me start with a short note about Fermio Masses. So when during the first class we brought down the Dirac-Lagrangian for a Dirac spinor, we saw that in the Dirac-Lagrangian we were adding a mass term of this type, where psi again was a four-dimensional Dirac spinor. And this, now we saw that it was allowed by Lorentz invariance, and everything was fine. And it was leading now to the mass term in the Dirac equation. But what happens if I have a fermion psi that is charged under our electroweak symmetry, so under SU2 left times U1? Then what happens to the mass term? Okay, so let's expand this mass term in terms of left-handed and right-handed components of the spinor, because I can always write down psi as a sum of left and right, in the sense that I can write down this simple identity where psi left is defined as the projector operator applied to psi, and then similarly, and then it's simple to see that indeed this is an inequality, and then for our mass term, we can write it down again as a sum of left and right. And this leads only to two terms, so the others are equal to 0. Namely, we have the combination of psi left and psi right, and the opposite one, psi right and psi left. Okay. All the other combinations are 0 because of the fact that we have to remember that if we apply p left and p right, and we get 0, the combination on orthogonal directions. So it's easy to see that if we use the Fermion representations of SU2 times U1 that we have seen yesterday, then all combinations are not gauge invariant. So in the sense that if I take any, psi left and any psi right, any left-handed or right-handed quark or lepton that we introduced yesterday, and we combine them in this way, then we don't get a singlet, or we don't get a singlet of SU2 times U1. Okay, so we cannot write down a gauge invariant mass for the fermions that we introduced yesterday. So that's the conclusion. Okay. But then the question is, no, we know experimentally that the fermions of the standard model do have a mass. Some of them are indeed very massive. And then the question is, how do we write a fermion mass term? Okay. Also, to introduce a little bit of jargon, what we say is that the fermions of the standard model are chiral, because as we have seen yesterday, the left and right components couple in a different matter with the gauge bosons of the standard model, and because of this reason, we cannot write down a mass term, an explicit mass term. Okay. So let's see what happens. So what if we introduce a new field? Let me call it phi. So this is a scalar field that does transform as a doublet under SU2, and it has a hypercharge equal to 1/2. Okay, so these are again the quantum numbers under SU2 left times U1 y. Okay. So if I have this new degree of freedom, actually I am able to show that I can write down mass terms for the fermions of the standard model. So in particular, I can add to the Lagrangian the following term. As an example, I can write down, I'm using the notation of yesterday for the fields. So I can take the left-handed quark, the doublet of SU2, I put that together with a scalar field that I just introduced, and then also together with the right-handed down quarks that we introduced yesterday. And this is a singlet, actually, under SU2 times U1. Just to give you a brief reminder of the quantum numbers. So this guy here we introduced yesterday, this was a 2 minus 1 6. This we just said that this is a 2 1/2. And this is a 1 minus 1/3. Now I'm taking the conjugate of Q left, so this is, yeah, okay, I already put the minus sign actually here, so this is for the conjugate of Q left. And then what you can see is that for the hypercharge, indeed, this sum gives us 0, that, is, this is telling us that we are, we don't transform under the U1 of hypercharge. And then also, we see that we are putting together two doublets. Let me write it down in a color. So we have two doublets, 2 times 2. And actually, we can show that if we combine two doublet representation, we obtain a singlet representation. That is what I'm interested to. And then actually also a triplet representation. But this to say that there is a way to combine two doublets to give a singlet, and this is the singlet combination that I want to put in my Lagrangian to have a term that is gauge invariant. Okay. So this term is okay. I can put it in the Lagrangian. It's also okay under the Lorentz symmetry. And if the scalar develops, a non-trivial vacuum, namely that at the minimum at the minimum energy of our system, we have phi let me denote this, the vacuum that is of the scalar field. If this is different from 0, or I can write this condition in components. So since phi is a doublet of SU2 with hypercharge 1 plus 1/2, I can write it down as, so these are the SU2 left components. Notice that this is the electric charge, because we have seen that electric charge is equal to T3 plus y, and then with the hypercharge we introduce we get these electric charges. So at the vacuum, at a minimum, we have the following configuration. We have a 0 here and some value that is non-zero here. So let me call it V over square root of 2, where this is different from 0. So we can rewrite this term of the Lagrangian using this vacuum. Again, I can write down explicitly the SU2 components. Let me put here a coupling constant. This is a coupling constant that is actually dimensionless. We can, check the dimensions. And so this is giving us your left, the left. Then we have 0, b over square root of 2, the right. And this we see that is leading to the following term in the Lagrangian, namely b over square root of 2, the right. And you can see here that this is a proper mass term for down quarks.
Excuse me, Stefania. There's a question by Sonali.
Yeah, go ahead.
Hi, Stefania.
Hello.
So when you're writing, phi develops a non-trivial vacuum, which is not equal to 0. So what does that mean? How it is not equal to 0?
Yeah, so for now, I just stated it. I will get into that in a few minutes. So maybe hold that question, and then if it is still not clear, maybe ask again.
Okay.
Yeah.
Sure.
But I agree with you. For now, I just stated it. I didn't explain how that happens. I just said, suppose that this is what happened, and then we get this mass term.
Yes. So that was just abstract, actually. Yeah.
Yeah. Okay.
Okay, thanks.
Sure. So you see that using this additional field that I introduced, this scalar field, I'm able now to write down a mass term if this field has indeed a non-trivial vacuum configuration. Okay. So that's the conclusion of this little exercise. Of course, I can also generalize it, and then what I can write down is the Yukawa Lagrangian. That is a new piece of the standard model Lagrangian that we didn't introduce yet. Namely, I have the term that we just introduced, this term here, but then I can also write down two additional terms that are gauge invariant. Namely, I can write down this term here with a phi dagger, you're right, and then one term that will generate the mass of our charged leptons. So this is all I can write down based on gauge invariance using the Fermion fields that we introduced yesterday. And note that with the fermions that we know of, we cannot write a mass term for neutrinos. Okay. because, yeah, this term here is simply giving us a mass for charged leptons, but we don't have the corresponding one for neutrinos. Okay, so this is already telling us that this mass Lagrangian, this Yukawa interactions means something if we want to explain the observation of neutrino masses. And this, as I already anticipated, we'll discuss a little bit on Friday. I mean, a little bit more on Friday. Having said this, let's go back to the question of, I think Sonali is your name. So how to achieve a SU2 left breaking minimum. So I will explain what I mean with this. So we want to see how to achieve a vacuum configuration of the Higgs that is non-trivial, as I was introducing. So the first part of the exercise is understanding what type of Lagrangian I can write down for this scalar field phi. So let's see what I can write down based on Lorentz and gauge invariance. So first, I can write down a kinetic term for this scalar field. So I have to use, the covariant derivative, and this follows, exactly the discussion that we have seen yesterday for the other fields of the standard model. So this will be a covariant derivative that contains terms with the gauge bosons of SU2 times U1, so namely what we call A mu and W mu A. Okay. And then we can, using the tools that we discussed yesterday, we can show that this is indeed gauge invariant. But then I can also write down an additional term that is the potential for the scalar V of phi. That will be a scalar function of phi. So let's see what terms I can plug in. So I can write down a term like this, where this will be a phi dagger phi. In terms of dimensions, mu has a mass dimension equal to 1. But this is actually not a full story, because I can also add a quartic interaction of this type, where this lambda is a dimensionless coupling. Okay. Now you can see that for a phi that is a doublet and that has some hypercharge, both these terms are gauge invariant. I don't have to, to worry about having something that transforms under SU2 times U1. So in principle, I'm allowed to put both of these two terms. And actually, we can check that if we want to write down terms that have a dimension up to 4, a mass dimension up to 4, these are the two only terms that I can write down in my Lagrangian, in my scalar potential. Okay. Now, this is a scalar function, and we can study it and see where this potential develops a minimum. So first, let me write that this is gauge invariant. I already said it in words, but so what we can do is to minimize V of phi. This is a relatively simple exercise, and I can write down, I know that phi has, since it is a complex SU2 doublet, it has it is composed by 4 real scalar fields that I can write in this way, just in components. And what I can see, what I will find is that actually the minimum of the potential corresponds to 2 mu square over lambda if mu square is bigger than 0 and also lambda is bigger than 0. So of course, I mean, this is a potential that is multidimensional, but at the end of the day, you know, if you have these 2 conditions that are satisfied, I'm really bad at drawing, but you will have a potential like this. Well, and this is you know, your Higgs field vacuum expectation value. Okay. And this is actually this quantity here is what I defined earlier as v square over 2. So this is what I denote. So this is our vacuum expectation value of the Higgs boson. Okay. So obviously this is a very brief discussion about you know, having this Higgs SU2 doublet developing a wave, but hopefully, you know, it gives you a bit of an idea of how to achieve a theory with a minimum that is non-trivial. So Nali, what do you think? Is that a little bit better now, or? Are you muted, or maybe the hand is like the thumb up, I guess. I don't know. But yeah, there is also another question.
Okay, so let's proceed with Pinat.
Hello, ma'am.
Yeah.
Yeah, ma'am, what's the reason behind taking the form of potential like this?
Sorry, I didn't hear you.
Can you speak
up
louder?
a little bit? Yeah.
Yeah. What is the reason behind taking the potential form of potential like this?
So this is again the usual reason that we want to write down something that is Lorentz invariant, but for a scalar this is a trivial task. And then also we want something that is gauge invariant. So suppose that so let's write here. So the conditions are Lorentz, gauge, invariance, and also I want to have operators, so terms in the Lagrange that have a mass dimension that is up to 4. Okay. So if I want to have terms in the Lagrangian with a dimension up to 4, in principle I can only write down terms like this or square, or, you know, I mean, this is trivially what I can write down, and then combinations like this or this and so on, right? But then if you look at all the other extra terms that I didn't write down here, say, I don't know, take this term here. What you can show is that this term is not gauge invariant because this phi field is a SU2 doublet and it has an hypercharge that is different from 0. So if you impose gauge invariance, you will see that these are the only 2 terms that you can write down in your scalar potential. And then, you know, in front of these 2 terms, I'm putting some coefficients that in principle I don't know. There can be anything at this point. I mean, at this point of the discussion. I just know what is the mass dimension of these coefficients in front. Does it clarify your question?
Yes, yes. Thank you, ma'am.
Okay, sure.
All right.
And then if the requirement is to have a vacuum that is non-trivial, what we found is that we need to satisfy also these conditions. So the signs of these coefficients of these operators are fixed. Okay, otherwise either you get a potential that goes to -infinity at for large field configurations, in the case of lambda that is smaller than 0, or you get a simple potential that has a minimum at 0. So these conditions here are necessary to have a non-minimal vacuum, a non-trivial vacuum.
All right. I think Sonali has still a question, so let me unmute her.
Yeah, hello.
Hey, yeah.
So when you write phi not equals to 0, that means lambda is greater than 0 and where the Higgs field is coming into the picture, right?
Correct, yes.
Okay, yeah, I understood. Thank you.
Okay, sure. Okay, very good. So now that we have this, let's see the appearance. Let's discuss the appearance of the Higgs and W and Z particles. So far, what we have is this scalar field, phi, and then also you remember from yesterday we had the gauge. Actually, I called it B mu. Sorry, different notation, but this was the hypercharge gauge boson, and then we had the gauge bosons of SU2.
Excuse me, Stefania, could we take another question, because probably it refers to the previous discussion from Manuel?
Hello, thank you. I have a question regarding the symmetry breaking mechanism. Shouldn't we break to SU2 cross U1, because you wrote we break SU2?
Yeah, thank you. What did I write? But yeah, right, that I broke SU2. But yes, I fully agree. It's a little bit sloppy. Yeah, let's see. So U1Y breaking.
So there isn't a difference in breaking the SU2 or SU2 cross U1?
Yeah, so in this case, so we'll see that indeed we are breaking a combination of this group, of the SU2 times U1, and this we'll discuss right now. But we see that U1, the hypercharge is also broken because the gauge group that is left unbroken is a different U1, is the U1 of electromagnetism, that is a little bit different than the hypercharge, as we'll see in a moment.
Okay.
Yeah.
Thank you.
So in this sense, yeah, you are breaking both. Just that something will be left unbroken, as I said, as we'll see in a second.
All right.
Okay, so these are the fields that we have and that we discussed already today, yesterday and today. But now let's see how we get to the Higgs particle, W plus minus, and Z. Okay, we want to understand this step. So to do so, it's pretty convenient to write down the scalar field in, I would call them polar coordinates, in the sense that you see that we started, and I wrote it down above, the field configuration like this. And now I can write down explicitly the minimum this way. So this phi 1 to 4 are real scalar field, so new degrees of freedom that I'm adding to the Lagrangian of the standard model. But actually, we can write down this field in a more convenient way, namely in the following manner. So I put here in front the vacuum expectation value. I have the two SU2 components. We put them here, 0, 1. And well, let me write, sorry. Let me write first the exponent of I pi I of x v sigma I over 2. So let me write the full expression and then I will discuss it. 1 plus hx over v. So let's see what is this this beast. So these are our Pauli matrices that we know of. So as you see here, I'm putting some fields. So these are real scalar fields. And I have 3 of them, one for each Pauli matrix. Okay. And then I know that, you know, my complex SU2 doublet scalar field has 4 degrees of freedom. Here I put 3, and then I have here one more. And this is another real scalar. Okay. So that's just a different way to write down my SU2 doublet scalar field. And then what we can do is to take the Lagrangian that we wrote above. So to take this Lagrangian here, L of phi, and then plug in this expression for the scalar field. So if I take the term, the kinetic term, and I replace phi with its valve, what I can show is that I get the following terms in the Lagrangian. So I will have a term like this. And then I have another term that looks like this, G W mu 3 minus so as you see, so here I have the fields that we saw yesterday, okay? What you can recognize from here are simply mass terms. Let me write in a different color. Mass terms for the SU2 times U1 gauge bosons. Okay. Notice that you have these combinations here, right? So you see that you're mixing the gauge boson corresponding to the third component of the SU2 isospin, and the gauge boson corresponding to the hypercharge. So this shows, you know, that we have a theory, a unified theory for electroweak interactions, where basically your SU2 left and U1Y are on the same footing because, you know, the third component of SU2 is just mixing with the hypercharged part. Okay. And this is, you know, we have, this is attribute, I mean, we have Glashow, Weinberg, and Salam. We introduced this unified way of looking at the electroweak symmetry of the standard model. Okay. Now, of course, you know, we can you know, diagonalize the system and find eigenvalues and eigenvectors and so on and so forth. And then what will come out are the physical gauge bosons that we know of, namely the W boson, W plus minus, and the Z boson and the photon. So I can diagonalize the system. So I will have the appearance of the Z boson and of the photon. This is the photon. that are linear combinations of this W mu 3 and B mu. So we'll have this is an angle that multiplies my W mu 3. And then I have sine of theta, W mu 3 plus cosine of theta, B mu, where this theta is the Weinberg angle. So we can show that the sine of theta is given by a combination of gauge couplings of SU2 and U1y. Namely, you have this combination here. So the gauge coupling of the hypercharge over the square root of the sum of the two. And then we can compute, the masses of these two gauge bosons, and we find that actually the mass of the photon is equal to 0, and the mass of the Z, let me write the square, is equal to V squared over 4. We did expect, and indeed, that this is proportional to the vacuum expectation value of the Higgs. And then you have this combination of couplings. So it's quite, remarkable, and is that we get a degree of freedom, namely the photon, that remains massless. And this, for a little bit more for the airspace, this is the field. So A mu is the field that corresponds to the unbroken generator. In the sense that we have, as we said already many times, we were starting from this gauge symmetry. We showed that the Higgs field is breaking this symmetry. But then actually there is a remnant, so a gauge group that is not broken by the Higgs field, that is the U1 electromagnetism. And the generator, as we mentioned, I think yesterday, so the generator is given by the combination of T3, that is the third component of the isospin, plus Y, that is the hypercharge. Okay. So let's done this here. That's why basically, when we introduced for the first time the hypercharge, we connected to the electric charge in this way, but there is really a reason. So this type of breaking that is coming from the electromagnetism, from the Higgs mechanism. Okay. And so this is for these two gauge bosons, the photon and the Z boson. And then I can also look at the other two. Let me put here an arrow. So we have this W1 and 2. You see that there are already mass eigenstates, but I want to build something that is also an eigenstate of the electric charge. That's why I define W mu plus minus eigenstate of the hypercharge as the combination 1 minus plus I 2 over square root of 2. And then we can show that the mass of this particle is equal to G squared over 4 V squared, again, proportional to the vacuum expectation value of the Higgs. Okay. So going back to our initial cartoon, so if we look here, so what happens is the following. So here, in terms of number of degrees of freedom, we're starting with 4 degrees of freedom for the Higgs field. And then these were massless gauge bosons, and therefore they had 2 degrees of freedom each of them. Okay, like a photon where you have two polarizations. We ended up after this Higgs mechanism with 1 degree of freedom. That is this Higgs particle here. That we introduced when we were writing down this scalar field. And then we had, well, I should obviously add the photon. We had these 3 fields here that were acquiring plus 1 degree of freedom because they are getting a mass, and therefore they are getting 1 additional polarization. Okay. So you see that basically what I'm doing here is to reshuffle degrees of freedom. So sort of, the Higgs field is sort of losing 3 degrees of freedom in favor of giving the degree of freedom to the W and the Z boson that are acquiring a mass. So what are the degrees of freedom that the Higgs field is losing? These are the pi fields that we write down here. And in fact, again, this is, if we want to go a little bit more into the details of the Higgs mechanism, these are called Goldstone bosons. I don't have much space, but these bosons have the nice property that they disappear from the Lagrangian in a particular gauge that is called unitary gauge. So basically, I don't plan to go into the great details of this statement, but what I want to say with this is that you can use gauge transformations, so this SU2 times U1, to go to a gauge in which these pi fields do not appear anymore in your Lagrangian. And in fact, these are the degrees of freedom that we are losing because they will appear as a longitudinal polarization of these massive gauge fields after electroweak symmetry breaking. Okay. Is there some question or?
There's a question in the chat by Nitesh, which says, is there any geometrical interpretation of the Weinberg angle?
I'm not sure what it means, geometrical interpretation, but so the Weinberg angle is just parameterizing how much this third component of the isospin and hypercharge gauge boson are mixing. Yeah. Okay.
Yep.
Okay, excellent. So the conclusion of this is indeed, we explained in very briefly the Higgs mechanism and the appearance of massive gauge bosons, and then also mentioned a little bit what we mean with fields that sometimes you hear that some fields are getting eaten by the gauge bosons, and this is a sort of a colorful way of saying that we have some fields that are the Goldstone bosons that indeed are can disappear from the Lagrangian in favor of longitudinal polarizations of gauge bosons that get a mass through this mechanism. Also, the last note that I wanted to mention in this context is that if you look at this at these masses that I wrote down, so that the mass of the Z boson and the mass of the W boson, and also actually you put together with the information on the Weinberg angle, you find a nice relation, namely you can define what we call the rho parameter, and that is given by the following combination of masses and Weinberg angle. And you can see using the equations that I gave you above, that this is equal to 1. And this is related to the custodial symmetry that maybe we'll have time to discuss today. So related, and this is a symmetry that I mentioned at the very beginning of this course, and we'll discuss a little bit later today or tomorrow, just briefly. Okay, but this is to notice since I wrote down the several masses and Weinberg angle in this slide. Okay.
Maybe it's a good moment to take a break. 5-minute breaks if you are or you're in the middle.
In 2 minutes. I have one more thing actually. So we have achieved all of this, studying the kinetic term of the Higgs field. Okay, once that we replace the Higgs with a vacuum, but then also from this kinetic term, I can plug in, so use this expression for phi, and then we can extract the couplings of the Higgs particle with the gauge bosons, so with the Z boson and the W plus minus. And this is a good exercise we can do that we can do at home. Can give you the answer because this is something that I will use in the second part of the class. Namely, what we will obtain are couplings of this type where you have 2 gauge bosons and the Higgs. So if you put here the W boson, you get this coupling scale like the mass of the W boson. Similarly, you can do the same thing for the Z boson. And now you will have a scaling with the mass of the Z boson. And then you have also 4-point interactions, so between 2 gauge bosons and 2 Higgses. So you have W, W, Higgs, Higgs, and this is again proportional to the mass of the W. And then finally Z, Z, Higgs, Higgs, that is proportional to the mass of the Z. So the reason I'm showing you this is that, okay, this is a good exercise to do, and then also because we learned that the couplings are proportional to the mass, or mass square if you want. Okay. So we learned already from here that the Higgs couples more to more massive particles. Okay, so that's what I wanted to say to complete the discussion of this part of the Higgs Lagrangian. And yeah, we are ready for taking a break. Or I will also take questions if
I see that there are a couple of questions, but I suggest that we take them after the break because maybe there will be many others.
Sounds good.
Okay, so let's stop for 5 minutes and then we take the questions and resume.
Yeah, very good.
All right. Maybe we can resume taking some questions. So the first, okay, so we have a question by Vangelis. Please go ahead.
Yes, thank you. I would like to ask about this custodial symmetry. What exactly is this?
Oh, yeah, as I was mentioning, I plan to discuss it either at the very end today or at the beginning of tomorrow. Just very briefly, this is a approximate global symmetry of the standard model, and yeah, we'll chat more about it. Yeah, sorry, I'm just delaying the question, but I'm planning to discuss it. So,
if it's possible, I would prefer tomorrow, because later today, kind of so.
Okay, I'm going slow, so it's very probable.
Okay, thank you.
The lectures are recorded anyways.
Yeah, that's right.
Evangelis, so you can check it later. So the next question is by Abid.
Yeah, hi, Professor Gori. I have a couple of questions. From the linear combination of Z nu and A nu that you have written. So my question is, first, I want to clear one thing for my understanding, that out of those 4 degrees of freedom, 2 of them was eaten by W plus and minus, and they acquire mass, and third one is eaten by G boson, right?
That's correct. Yeah, that's right.
And remaining one was the observed Higgs boson in experiment.
Correct. Yeah, exactly right. Yes.
Yeah.
Yes.
So, my question is that linear combination you have written for Z nu and A nu, is it fixed that linear combination that Z nu is always written with the negative and A mu is positive, or can't we flip it? Is it random?
Yeah, no, it's written that way. Simply when you diagonalize, you find the system and you find eigenvectors. You have that combination if you define the angle in this way with this choice of signs, and it's something that you can check it. But yeah, that's right. It's coming from here. You see, you have this minus
Okay.
for the way that you that we have defined these interactions, and then yeah.
Okay. Okay, and another question. I'm expecting one mathematical step, if I'm not wrong. That how is there any steps to derive that mz square expression that you have written?
Yeah, that's right. I mean, the only thing I'm doing here, I mean, I'm not showing the steps, but is to take this Lagrangian, this part of the Lagrangian here, and then I want to find the eigenvectors and eigenvalues of this Lagrangian, and then one of the eigenvalues is given by this mass square here, that correspond to the Z mu eigenvector that I wrote down here. Yeah.
Okay. And my last question is about the Weinberg angle, that this weak unification of this theory is dependent on parameters. There are Weinberg angle G and G prime. Those G, one of G is constant. That is, I think, electromagnetic coupling constant. So my question is, how many unknown parameters were there at that time when this theory was developed? Means all.
Yeah. So as I think we mentioned yesterday, so there are only 2 for the electroweak interactions. There are only 2 coupling constants that are what I called here G and G prime, and this is then fully defined, fully defining my gauge theory before electroweak symmetry breaking. So these are the only 2 parameters that are in the game.
Okay. I apologize because yesterday I was not present because of power load shedding problem.
Oh, sure. Yeah, of course. Yeah.
So without measuring Weinberg angle and one coupling constant, we cannot predict the Z mass, right? At least we have to measure one parameter experimentally.
Yeah. So in this term, so the mass is generated after electroweak symmetry breaking. So you have also an additional parameter in the game that is this VEV, and this VEV is in the standard model doesn't predict the VEV, so we need also measurement of some mass to determine this web. So on top of these gauge couplings that I was mentioning, this G and G prime, after electroweak symmetry breaking, you have also this web that is an unknown. So you need some additional measurement to determine it.
Okay. Yeah, that's right. Because from this theory, we can predict the mass of jet by knowing the value of G and G prime. But what about V? Because that expectation value is the vacuum expectation value.
Yeah, that's right. Yeah. So also that is something that we don't know from the theory point of view. So as I was mentioning, so we need the measurement in such a way to determine this V.
Okay.
Yeah.
Okay. So we have to measure the V from known parameters. Okay.
Yeah, that's right. Yeah.
Okay.
Yeah, correct.
Okay.
So at the end of the day, I mean, we'll mention this a little bit, but so for example, at LAP, the E plus E minus collider running in the past, we had many measurements, including the Z boson mass or the Z couplings to fermions, and then the idea is to do a global fit of all these measurements and then extract informations about the coupling constants. I mean, this G and G prime and the web that are unknown in the standard model, in the sense again that the standard model is not telling us what is the value of these parameters. These are just free parameters of the standard model.
Okay. My last question is from that equation QEM. Is that a Gell-Mann-Nishijima formula for electroweak and similar equation?
So I have to say I don't remember that equation. So the Gell-Mann, but it can be. I have to check. I don't remember the name.
Okay.
Yeah, here I represented it in terms of where was it? Yeah, this equation here that is determining the generator of the group that is not broken by the Higgs vacuum expectation value.
Okay.
Yeah,
because I think Y is simply hypercharge, right?
correct.
Yeah. I think because of that I have a doubt, because this equation looks similar to Gell-Mann-Nishijima, but there it was, I think Y by 2 was there.
Oh, so these factors of 2, so sometimes in books you find these 2, I think, or that, yeah, it's a matter of normalization. Sometimes the hypercharge is defined with a factor of 2 compared to these nodes, sometimes not. As long as everything is consistent, it doesn't matter.
Yeah. Okay, thank you.
Mm-hmm.
Okay, next there is a question by Sri Rupa.
Hello.
Hey.
Yes, can I ask my question?
Yes, please.
Yeah. Is it possible to estimate the relation between Higgs mass and its vacuum expectation value in standard model physics?
Yes, we'll get to there in a bit. I will say something about it. Let's delay a little bit this question, and then we chat again if there is something not clear. Yeah.
Thank you so much. I had another question, but I asked in the chat box, and it was answered. But still, I want to check it again. That actually, I was trying to calculate the rho parameter in case of beyond standard model using 2 triplets Higgs scalars, and one of them was having a complex VV. Now, someone in the chat box suggested that using that U1 symmetry, we can choose always the vacuum expectation value to be real. But in my case, I'm actually having a complex VB. I don't know if I need to use the real component of the VB in the rho parameter calculation, or I should use the modulus only.
Okay, so it depends a bit on the question. So in the standard model, so what we are discussing in this course, indeed we have freedom to choose, give me a second. So we have some gauge freedom in such a way to gauge and also rephasing freedom in such a way to choose the vacuum expectation value of the Higgs of this form, in the sense that is on the lower component of the doublet and is real. So this is for the standard model. Now, if you go beyond the standard model, sometimes it's not true. So sometimes you might have like vacua that are much more complex. I mean, so sometimes you can have vacua in that are breaking different type of symmetries, including CP. So that one has to be a little bit careful. So I don't know the exact model that you're considering, but sometimes it can be that the vacuum is not as trivial as as in the case of the standard model.
Particularly, I'm working with two triplet Higgs scalars, and one of them aqueous vacuum expectation value complex.
Yeah, it can very well be that then you cannot get rid of that, contrary to the standard model. Yeah.
Okay.
But yeah, maybe we can.
Okay.
I mean, we can chat a bit more later or also offline about this, because this goes pretty much beyond what we're discussing here. That is the standard model, but it's true that is it can be much more involved than in the standard model case, where the vacuum structure is pretty simple.
Okay, ma'am. Thank you so much.
Okay. So if there are no other questions, there are a couple of more things I wanted to mention before entering the discussion of the Higgs phenomenology. Namely that, so there are, now that we found finally the W and the Z bosons, we can compute all the couplings of, for example, the fermions with these gauge bosons. So we'll have a fermion W or Z couplings. And again, this is a good exercise to try to compute these couplings, and they all come from covariant derivatives. So we saw that if you take a fermion, again, psi I of the standard model, then you have terms in the Lagrangian like this, and these are indeed inducing fermion couplings to W and Z. And what you can show is that, again, I would suggest to compute this at home, is that the Lagrangian will contain terms like G over the cosine of the Weinberg angle, Symmio, and then you have the several fermions of the standard model. Then you have here T3 minus sinus square of theta, the electric charge of the fermion, and then psi I. So this is the coupling of two fermions and the Z boson. Then you have couplings with the W bosons that look like this. This time, as we have learned several times, this is only for left-handed quarks and the leptons. That's why I'm putting here a left. And then we have also couplings with the photons, with a photon that is given by the electric charge, and then a mu, and then a vector coupling gamma mu psi I, where this electric charge, actually I didn't define it, but you can show that this E, that is the electric charge of the electron, is given by G, that is the SU2 coupling constant, times sine of theta. Okay, as we said, everything can be expressed in terms of this G and G prime. So that's what we are doing is now writing down the full Lagrangian of the standard model after electroweak symmetry breaking, because now we have really all the ingredients for doing so. So we can generate all the couplings that then we can test experimentally. Okay. Yeah, I see there are some there is some question.
Yep, let's take them. So the first one by Sri Rupa. Please go ahead.
No more question. I forgot to just lower my hand.
Okay,
sorry.
okay. So there are no more questions, I think.
Okay. And then a last comment, maybe, yeah, let's not go much into the details, but I wanted to mention this because it's a very important aspect of everything that we are discussing, is that we have presented a lateral symmetry breaking that is happening spontaneously in the standard model. Actually, yeah, I should write down this somewhere. So spontaneous. Yeah?
Maybe let me pass you a question because it was missed before by Shantanu. Please go ahead.
Hi, Professor Good.
Hello.
Yeah, so I need to ask you a very simple question. I'm wondering, there's some coupling between G boson and Higgs. So, two G boson and Higgs couple to each other and give us a vortex factor. So we can calculate them, but two Higgs doesn't couple with G boson. What is the reason behind that?
You can see it also based on gauge invariance if you want, and then it comes out once that you expand this covariant derivative, if you do it properly. Yeah. Okay. So what I wanted to mention is the following. So suppose that we don't know anything about the Higgs mechanism, and but then we do know from experiments that the double boson has a mass. So if no Higgs mechanism, but the double boson has a mass somehow, coming from some unknown source or some unknown UV physics, we end up actually having a problem. So namely, what we can do in a theory like this, so the standard model of particle physics, as we have learned until yesterday before lateral symmetry breaking, but with a massive gauge boson, then since the double boson has a mass, what we can do is to compute the scattering of two longitudinally polarized gauge bosons. So WL, WL, so this longitudinal polarization. So we can compute the cross-section for two longitudinally polarized double boson to go to two of them, okay? And so we can compute this process in the standard model without the Higgs. And we end up having a problem, namely that the matrix element that we find, summing over, all the diagrams contributing to this process, scales like some coupling constant square, S, that is the center of mass energy, over the mass of the double boson square. Okay. So this is a problem. You might wonder why this is a problem. The reason being that, you can think about doing the experiment. Studying your scattering and going to energies that are bigger and bigger, in principle, infinity. Okay. And what you see is that indeed this cross-section is blowing up. Okay, so that tells us that the theory is a certain point is not well defined anymore. So as we say, we have problems with perturbative unitarity. So meaning that if we go to arbitrarily high energies, so in the UV, your theories start to be being in trouble with unitarity. Okay. And so this is showing that, and we can compute what is the bound from perturbative unitarity, and we learn, so the bound is at energies not too far away from the TV scale. Let me call it 2 TV, just to give you an idea. So this tells us that we need something. So we cannot write down really the standard model theory without the Higgs, without something, you know, and with masses of these gauge bosons. Okay. And once that we introduce the Higgs, so this is, let's see, so this is the result without the Higgs. So with the Higgs, so once that we take the Lagrangian of the standard model that we have discussed during these 3 classes, this process will receive additional contributions, as for example, you will have diagrams like this where you have a Higgs boson in the middle, and now the cross-section is well behaved, in the sense that you don't have this problem of perturbative unitarity. Okay, so this was really a very, very, very strong argument to believe that the LHC, before it started running, had to discover something that was unitarizing this WW scattering. And because these are the energies tested by the LHC, and indeed, the LHC, as we all know, discovered the Higgs particle in 2012. Okay. So I can show you a slide about this. I find it pretty cute. So this is a slide. Let's see. You can see my screen, right? The slide. Okay, great. So this is a slide about the Higgs boson discovery. So, okay, this is a picture that was taken the day of the announcement at CERN for the 4th of July 2012. As you see written here, so this was done using really a small amount of luminosity at LHC. So only 5 inverse femtobarn or 7 TV data and 5 at 8 TV. And for comparison, now we have something like 140 at 13 TV. And these are the 2, plots. 2 of the plots that the 2 discovery papers by Atlas and CMS showed us. One for the Higgs decaying to 2 Z bosons and 2 4 leptons in the final state. We'll discuss a little bit the phenomenology of the Higgs, so we'll understand better why the Higgs decays in this manner. So what you see in this plot are really data. So this is, these are data points. And the invariant mass of the 4 leptons should give us the mass of the Higgs boson that was unknown before the Higgs boson discovery. And you see that at around 125 GeV, that is the mass that we have measured, we had this excess of events, this tiny bit, because you see that we had only a few events back then. And this was, in blue, in dark blue, you see what was expected by the standard model. Okay, and you see these 2 data points that are, giving us this small bump at around 125 GeV. And then similarly, we had the study of the Higgs decaying to 2 photons. And again, you see this small bump above the predicted background. And this was obviously super exciting, So having said that, so I can go back to my iPad. And what we want to do now is to study a little bit the properties of the Higgs boson. Let's see. Okay, so back to the iPad. So this is our section 3.4, properties of the Higgs boson. So we have to study the properties, we have to understand how the Higgs couples interacts with all the other particles of the standard model. We have already learned that the Higgs couples to the W and the Z in a way that is proportional to the mass square. Okay, so this is what we already mentioned. Then we might wonder about the Higgs coupling to fermions, so to quarks and leptons. So these couplings are coming from the Yukawa-Lagrangian that we have already introduced. So let me write it down again here. So this was our phi scalar doublet, Q left, and then what we can do is to replace this simply with the vacuum plus the Higgs particle. And then if we do this exercise, what we will see, for example, if you take, I don't know, this first term, you will have something like D left, then you have V plus H, square root of 2, D right. And you see that, so this term here is giving us the mass of the, in this case, the down quark. And here you have a coupling of the Higgs with down quarks. And this coupling is once more proportional to the mass. So this will be the mass of the down quark over V. Okay, and similarly to for all the other couplings of the Higgs with fermions. So we always find that it couples proportional to the mass.
Okay. Can I pass your question now by a bit?
Mm-hmm.
Please go ahead.
Yeah, my question is that Higgs couples to W1 or Z with proportional to this. So it gains mass before coupling or after coupling? Because if it's proportional to mass, then it should first interact with Higgs field, then acquire mass.
Yeah, so let's be a bit careful not to confuse the Higgs field with the Higgs particle. So the Higgs field is this phi here. Yeah. And then I'm writing all the couplings, and then I'm studying the vacuum and so on and so forth. And then, I mean, the masses are generated once I look at my theory at a minimum, and then I do electroweak symmetry breaking and so on. But then I have also this physical degree of freedom that is the Higgs particle, and we learned that the Higgs particle couples to the massive gauge bosons. Hopefully, yeah, it answers to your question, maybe.
That matter field couples to Higgs field, then it's acquire mass. I think it is the right statement. Then matter field couples to Higgs particle to acquire the mass. I think which one is right? That I want to clear.
Can you repeat the last part of the last question? Sorry.
Yeah, there are some confusion between the statement that it is the Higgs field which couple or fermionic field which couples to Higgs field then acquire mass, rather than Higgs boson which couples to the fermion to give the mass.
So it's the Higgs field. So this phi here. that is giving mass to the massive gauge bosons. And as a consequence of the Higgs mechanism, you get that you have a new degree of freedom, that is the Higgs particle that is coupled to the massive gauge bosons. But this is the Higgs field, so this phi here that I'm writing down here, that gives mass to the massive gauge bosons of the Standard Model.
Okay. My another question is from that Higgs couples to Fermion. Is it possible to couple Higgs field with any kind of that fermionic field which is acquiring more heavy mass or than Higgs boson? Because we experimentally know the mass of Higgs boson.
Yeah, so in principle, you can couple the Higgs to other type of fermions beyond the Standard Model. That's a possibility. Yeah, and those can also be quite heavy. Of course, I mean, if they are super heavy, then you have a problem of having a perturbative theory because your couplings need to be very large, because we know the vacuum expectation value of the Higgs.
Okay, yeah, I asked this question because already we have one massive fermionic field, that is our top quark field,
yeah,
and whose mass is much heavier than Higgs boson. So
yeah,
that top quark field is acquire mass through the same mechanism.
Right. Yeah.
Okay.
Yeah.
So so it is possible to gain mass with Higgs coupling through spontaneous breaking, even more heavy than the field itself, field quanta itself.
Yeah, in principle, yes. In practice, as I said, you cannot go too heavy because at a certain point you have couplings that are really huge. Yeah. And also at the same time, large couplings mean that most probably you're, in general, you have to agree with experiments, right? So if you have the Higgs couple that couples very strongly to some other particle, then you have to understand how you link this statement to experimental searches. So one has to be a bit careful not to be in tension with experimental analysis, but in principle, yes. Yeah.
Okay, so I can assume it that top quark mass is not quite acceptable according to this mechanism. Is this still a contradiction or some controversy?
No, I mean, the top quark mass is just it's just coming from the Higgs mechanism, and I mean, it's just this term of the Lagrangian, right? Once that you replace the Higgs with the VAB, and yeah, that's there is no problem here. Yeah.
Okay. Thank you.
All right. Next question is by Sonali.
Yeah, so this is a generalized question. I want to know that can we estimate how much amount of mass we are getting from Higgs? Like, for example, B quark mass is 4.65 GeV. So can we estimate how much amount of mass is coming from Higgs? Obviously, 100% mass we are not getting from Higgs, right?
For elementary fermions, that's the statement of the Standard Model, that the elementary fermion, the mass of the elementary fermions is coming from this Higgs mechanism. So yes, it is 100%. Yeah. For elementary fermions.
100% of mass is coming from Higgs.
Yeah, as I said, for elementary fermions, if you're thinking about, I don't know, the proton mass or whatever, then this is a different story. But if you're thinking about elementary fermions, yeah, this is the statement of the Standard Model. Yeah.
Okay, so it can be different for protons.
Yeah, that's right. Absolutely. Yeah.
Yeah.
Okay.
For protons, it's about 5%. The rest is coming from color dynamics, from confinement.
Okay. Thank you.
We have another question, I think, or not. Yeah, Abhi, do you still want to ask a question?
My
Please go
question
ahead.
is about the Higgs self mass. That how is there any explanation how Higgs acquire mass? Because other particles are
Yeah,
acquiring
so
mass.
I'm getting there right now. So just yeah, stay with me.
Okay.
Yeah, so indeed, so I was explaining the coupling of the Higgs with gauge bosons and fermions, and then we might wonder, are there other interactions of the Higgs? So other interactions of the Higgs. And actually there are other interactions that are coming from the scalar potential that we wrote down already. Here I'm writing down again for completeness. So what we can do is, as I said, we have this non-trivial minimum. So what we typically do is to trade these free parameters, so the standard model Lagrangian, with more physical parameters, namely the vacuum expectation value, V, and the mass of the Higgs boson that we have measured. So this is a simple exercise that we can do at home, and we have already seen the relation actually between V and mu and lambda. We can also extract the mass of the Higgs, and actually, we get this nice relation, namely that the mass of the Higgs square is also proportional to the VEV and square in this way. So we see that, we would expect to have the mass of the Higgs that is at around the electroweak scale, roughly speaking, so at around its vacuum expectation value. So having said that, once that we change these variables, we can rewrite the scalar potential for the Higgs particle. And what we find are these three terms. So you have a mass term for the Higgs, then we have a h to the third power type of interaction with this prefactor. And then we have a h to the fourth that is multiplied by the mass square over 8 p square. So the reason I'm showing you this is that, so first, some of you were asking about the mass of the Higgs, and we see that this is a relation with the vacuum expectation value. And then also we learned that we have Higgs auto interactions. So interactions of the Higgs with itself. So we'll have couplings like this and this. Okay. And then also what we see is that this type of potential, so the scalar potential of the standard model, is highly predictive because we know these coefficients as soon as we measure the mass of the Higgs and we measure the vacuum expectation value, at least indirectly through the measurement of the gauge boson masses. Okay, so the standard model is highly predictive. I mean, this is a general statement, but we are discussing this in this context of the scalar potential. Okay. And then let's think. Am I missing any other interaction of the Higgs with anything? Seems to be pretty much complete. But from these notes, we see that we don't have any coupling of the Higgs with massless gauge bosons. And this is the last bullet point I wanted to discuss in this context. So does the Higgs couple to photons or gluons? Okay. We might say no, because the mass of the photon and of the gluons is equal to 0. And then we have learned that the Higgs couples proportional to the mass. But then also we might say yes. So we have seen that the Higgs was discovered through its decays to gamma gamma, so to 2 photons. I showed you 10 minutes ago the slide. So, you know, we have to understand how we have this coupling, how to generate this coupling. And in fact, you know, the right answer is yes, just that we need to go beyond the 3 level in perturbation theory. So at 3 level, indeed the couplings are equal to 0. But at 1 loop, we can write down Fermion diagrams like the following, where you have a loop of quarks of the standard model, and here you attach 2 gluons. Here you have a Higgs. So you see that this is an effective Higgs gluon-gluon type of interaction. And then similarly for the coupling with photons, I can do the same thing. So I can plug in here the quarks of the standard model that are charged under electromagnetism. But then I also I have another diagram with the W boson that has also an electric charge. Here I put my 2 photons, and this is the Higgs. So these 2 diagrams are generating my effective Higgs gamma-gamma coupling. That is the coupling that was responsible for the Higgs decay to photons that we have discovered at the LHC. Okay. Now, let's see. So I got many questions. So what do you think? Can I continue a little bit the discussion for, or it would be
yes, continue a little bit if you.
Sorry, say that.
Yeah, you can take 5 more minutes if you wish, and then we take questions. Or
sounds
5,
very good.
10, whatever.
Yeah. So let me stop sharing my iPad, and then I want to show you a couple of slides again. But yeah, before doing so I wanted to, so that we don't lose track of what we are doing. So in this page here, I wrote down all couplings of the Higgs with the other standard model particles. And you see that, you know, once that we specify the masses, and we basically define all the couplings of the Higgs boson with any other particle of the standard model. And then we can start to make predictions for the LHC. And this is what I'm going to show you in this couple of slides. So what is the phenomenology of the Higgs at the LHC? So let's discuss a little bit the production and the decay of a Higgs particle at the LHC. So first, I want to mention that at LHC that we're colliding protons, the production of the Higgs is a very, very rare event, in the sense that we really need many proton-proton collisions in such a way to produce a Higgs boson. And in this histogram here, so what I'm showing is how many proton-proton collisions we need, so something like 10 to the 10, in order to produce a Higgs boson, either in what we call gluon fusion, that is represented here by this Feynman diagram, where basically, effectively, you're taking 2 gluons of the proton that you're colliding, of the protons that you are colliding to produce a Higgs through this Feynman diagram here. This is the Higgs glue-glue one-loop interaction that we just wrote on my iPad. And then we have also subbleeding production modes of the Higgs boson that are even more rare. So this is the vector boson fusion, number 2. We see the Feynman diagram here. So this is happening because of the Higgs coupled, the Higgs couples to the W and the Z of the standard model. And then we have the Higgs produced in association with the W or a Z. We have this Feynman diagram here called Higgs Strahlung. And then finally, we have here a diagram for the Higgs produced in association with 2 tops. And we have this diagram here, okay? So overall, you see that indeed we need incredibly many proton-proton collisions to produce a Higgs particle. So it's very low probability. But since we know, that we have incredibly many proton-proton collisions at LHC, indeed, we were able to produce quite a few of them. I think we are talking by now of a couple of millions or a bit more even. And so this is for the production of the Higgs at LHC. And then for the ones that we produce the Higgs will decay. It's not a stable particle. And then we can make predictions using the standard model Lagrange that we have studied Monday, Tuesday, and today. We can make predictions for the several probabilities of the Higgs to decay to whatever particle in the standard model. So in this plot that you see here on the left, I'm showing what are the Branchi ratios, so the several probabilities for the Higgs to decay as a function of its mass. Obviously, before the Higgs boson discovery, we didn't know the Higgs mass. And now we know, so we are here at 125 GeV. And what is interesting is that being here, you see that you have several of these lines that correspond to a Branchi ratio that is not too incredibly tiny. So we know that having this mass, we will be able to measure many of these decay modes of the Higgs boson. So you see that the Higgs is mainly decaying to BB bar, so 2 bottom quarks. Then we have the Higgs decay to WW, we have the Higgs decay to tau tau, charm, Z boson, gamma gamma, Z gamma, mu mu. So we have all of these that can be measured by the LHC, and we have very precise predictions from the standard model Lagrangian. Okay, so this is what we see in this plot. In the plot on the right, what I'm showing is the total width of the Higgs boson. Again, if we are here at 125 GeV, we see that the width is tiny, is like a few MeV. And this is telling us that the lifetime so actually the Higgs is decaying pretty quick. So as soon as you produce it, the Higgs also will decay. And here I leave a little exercise. So using the standard model Lagrangian that we have learned from Monday to today, we could try to compute the several widths of the Higgs into WW, ZZ, as well as fermions. So the fermion calculation is easier. So this is what I would start with. And then we can check that indeed we get roughly this type of decays, so this type of Branchi ratios. So this is for the standard model predictions. And then, yeah, I think we should delay to tomorrow. We would like to understand how we can match and we can compare the standard model predictions with data. So what the experimentalists are giving us, and what we learn using data on the Higgs coupling to the other standard model particles that we have introduced today. So that's, yeah, I think the task for tomorrow, for the first part of tomorrow. So I think I can stop here and take questions.
Okay. Perfect, thank you. So now we can go to the Q&A session, no? So, okay, that's what I was expecting, the recording stopped. So, any questions? Okay, so we have a question from Stefano. Please go ahead.
Hi. So you showed us how to have a decay of the Higgs in photons. You have it in your notes. And the second diagram involves the W boson and the photon. Well, the interaction between the W and photon, does it come from the kinetic term of the Higgs field?
No, it does come. So let me go back to the iPad. 1 second. Let's see. I think let's go back maybe to the notes of yesterday so that I can show you directly there. Let's see. Don't remember it was. If I find it, otherwise I will write it again. Okay, here it is. So yesterday, you remember that we introduced, so this is part of the notes of yesterday, we introduced the covariant, so the Lagrangian of a, that has a SU2 local invariance. And so you remember that we said that if we want to write down this term here in the Lagrangian, this f mu nu for the SU2, the corresponding SU2 gauge bosons, we need to add this term here in the definition of f mu nu. Okay, and this will lead to 3-point interactions and 4-point interactions. And this is basically the starting point of that. Of course, you have to work a little bit because then, you have to redefine, you have to define the W plus minus and so on. So you have an SU2 times U1, but it comes from this type of terms. Yeah. And so the Higgs has nothing to do with that. So for this coupling here that you were mentioning. So this is the coupling that you were talking about, right?
Yeah. Okay, thanks.
Mm-hmm.
All right. Next question by Fenway. Please go ahead.
Hi, Stephanie. So I have a questions about the group theory. So can you give me more details about 2 cross 2 equals to 1 plus 3? Yeah, I'm not understood.
Sure.
This notation. Yeah.
Let's see, where did I write it? 1 second. Okay, here it is. Yeah, so so first let me give you a reference and then I will mention a few things. So there is a nice book by Georgi. I don't remember exactly the title. It's something like the algebra in particle physics or something like this. Particle physics, roughly. I am not sure about the title. Let's put roughly this. Where this is a very good reference if you want to learn more about Lie groups from a particle physics perspective, not for mathematicians, if you want. So going back to your question, so here the idea is so you have 2 doublets, just generic doublets that I can write down in this way, and then you have to understand what type of products you can do between these 2 doublets. Okay, so one thing you can do to put together these 2 doublets is to build a singlet. So you can build the singlet simply doing the scalar product between the 2 doublets. So you will have, let's see, terms like this. And what you can show, so we have introduced SU2 transformations. And what you can show is that if you put together the 2 SU2 doublets in this way, so with the scalar products, what you get out is a quantity, an object that transforms as a singlet under SU2. Okay. But then this is not the only possibility because in principle, you can put together the 2 doublets using the epsilon tensor. And if you do so, you can again demonstrate that you get a triplet representation of SU2. So that once that you do a SU2 transformation on this object, you get something that is transforming, that is not a singlet. Yeah, so this is what I meant with this 2 times 2 that is equal to 1.1 plus 3, so that you have 2 possibilities of building a representation that is either a singlet or a triplet. But yeah, you can find many more details, obviously, in this book if you want to learn more about Lie groups for particle physics.
Yes, sorry, I just mute myself. Thank you. So another question is, another question is about the diagonalize of the W boson. So when you calculate the eigen vector of the W boson, so can we just use W mu1 and W mu2 as the eigenstate for the W boson instead of the combination?
Yeah. So indeed, this W mu1 and W mu2, they are mass eigenstates, as you can see from here and here. So from that point of view, it's perfectly fine. The problem, the reason that you don't want to use those is that they are not eigenstates of electromagnetism. Since electromagnetism, so this U1 of electromagnetism is unbroken, you would like to work with fields that are eigenstates of this quantum number. That's why we define these 2 combinations here, and these 2 combinations are indeed eigenstates of the electric charge. That's why we do that, not to diagonalize masses, but to have something that has good transformation properties under electromagnetism. Okay, great. Other questions?
Yeah, next question by Abhishek. Please go ahead.
Hello. I have a question related to the Higgs field. In the Higgs field, we actually have 4 real degrees of freedom, right?
Right.
And when the spontaneous symmetry breaking happens, 3 of them are eaten by the gauge bosons. And so when we are working above the energy scale of electroweak, I mean, when the symmetry is not broken, do we explicitly see these extra 3 degrees of freedom in the detector, or do we have any signal that says these
so
are
so at the energies that we are testing in our labs, we are working, we have electroweak symmetry breaking, and then we have all the masses of the gauge bosons and so on. So the energies that we are testing are energies where the electroweak symmetry is broken. So you can ask the same question from a cosmological perspective, and at a certain point, you restore the electroweak symmetry in the early universe, and then this is a different story. But for the for now, for the nature that we are studying today, then electroweak symmetry is broken, and then we don't have these Goldstone bosons in the sense that we have the W and the Z that are massive with a longitudinal polarization.
But currently, we have experiments being conducted at 13 or 14 TeV, right, which is above the electroweak scale. So do we not see these massless scalar fields?
No, the electroweak symmetry is broken at those energies. It's. When you measure the, you have your W and Z boson that are massive at those energies. Yeah.
So at which scale do we have gauge boson to be massless then?
Oh, yeah, I think, Joan, you know the answer to this better than
I got distracted by the question. The question was?
My question is, when do we have these gauge bosons of electroweak symmetry? I mean, SU2 become massless. I mean, what is the exact energy scale? Is it 150 GeV, which is the electroweak scale, or
no? So they are always they are always massive. However, at high energy, at very high energies, it could be a good approximation to neglect the masses. There is no more than that.
Yeah, just that, I mean, I was linking that to a cosmological question that you have in the early universe where you don't have electroweak symmetry breaking, and you're at very high temperatures. I don't remember the exact, phase transition, but, when it happens, but it's, you have to go
the phase transition.
Yeah, that's right. So this is, this is something I was mentioning, because otherwise, I mean, for our purposes, as I said, for laboratory tests, you have always massive W and Z bosons. Sometimes, as John was mentioning, sometimes for a matter of calculation, it's useful to maybe neglect the masses because they are a little bit smaller than the energies that you are testing, as you were saying. But electroweak symmetry is still broken.
So when the symmetry is restored, do we not see the scalar field then? So do we always have to assume that W bosons are massive even at 10 to the power of 10 GeV? Is that what you're saying?
Yes, yeah, that's right.
Okay.
Yeah.
So it's not just by electroweak symmetry breaking. Okay, I get it. I think I understand it now. Thank you.
Okay. Sure.
All right. Next question is by Abid.
Yeah. Hello.
Hello.
Yeah, my question is about the left-handed and right-handed component of the fermionic field. When we are saying that fermions acquire mass through the Higgs coupling, so we are specifying especially the left component of the fermionic field, right?
Yeah, so the mass terms are always combinations of a left-handed field and the right-handed field, as you can see from here. Let me highlight the. So you see that I'm taking a left-handed field and the right-handed field. Okay. I don't know if that answers your question.
Yeah. My question is, when we are talking about the group symmetry in electroweak, we are talking about SU2L, that is the left-handed fermionic field. So that is my question. So what happened with the right-handed fermionic field?
Yeah, so the right-handed fermions don't couple to the W bosons, as we were mentioning yesterday. So that's the reason that the theory, the standard model theory, is chiral, in the sense that the left-handed fermions are different from right-handed fermions. They couple differently. But then your Scalar symmetry, so the fact that the left and right fermions are different is broken by the fact that you are introducing this mass term, this type of mass terms that are putting together left-handed fields and right-handed fields.
Okay. So Higgs field is not coupled to right-handed fermionic field.
No, it is. You see this combination. So if you write it explicitly, as a maybe let's see it here. I brought it down again later in the notes. Yeah, so if you take these three terms in the Lagrangian and then you replace the phi field, what you will end up having are couplings like this, where you have a D left and a D right. So basically, this will generate a coupling like this, right? D right and the Higgs. So you see that the Higgs couples to a combination of a left-handed field and the a left-handed fermion and the right-handed fermion all the times.
Okay. 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 My next question is that even in left-handed field, neutrinos are very exceptional compared to quarks. Like both quark and leptons, they are present in doublet, right? All the 6 generation of quarks and lepton. But neutrinos are not acquiring mass through Higgs mechanism. Although electron, muon, tau acquire through the same mechanism. So yeah, so my question is, being left-handed neutrinos, why they are not acquiring mass? I think they have different mechanism for mass generation.
Yeah, that's right. So we'll discuss more of this on Friday. But just one word is that if you add sterile neutrinos, then you can write down couplings of the Higgs with neutrinos as well. Just that you need to add these additional fields in such a way to be able to write down a Yukawa like this for the Higgs field. But we'll see this better on Friday.
Okay. Thank you. Thank you. Anyway, it's a very nice presentation.
Okay, very good.
Okay, I think we have one last question that we could take, and then I think we should leave, no? By Abhishek, last one.
Sorry, I already asked the question.
Okay, because your hand was still up. Okay, so then we are on time and we are done for today.
Okay, great. Yeah.
So many thanks for the lecture and see you tomorrow.
Yep, see you tomorrow.
Ciao, ciao.
Thank you for the questions. Bye.